Welcome. This video is going to continue looking at problems from Section 2 in Chapter 1 of the Brown SL Chemistry book. So starting with question number 23, you're asked to determine the empirical and molecular formulas, and you're told benzene is a hydrocarbon, a compound of carbon and hydrogen only, with 7.744% hydrogen by mass. So by reasoning then, that means the other 92.26% or grams has to be carbon, since that's all that's in is carbon and hydrogen. So I could go ahead and take my given percents or grams, divide by the molar mass, and I see that I have 7.663 moles of hydrogen, and then the 92.26 is going to yield 7.682 moles of carbon. And if you go ahead and divide those, you will see that within sig figs, that gives me an empirical formula of just CH. So then if the empirical formula is CH and the actual molar mass is 78.10, how do I get from this empirical formula to the molecular formula? Well, that's actually the easy step if you don't remember these, because CH would give me a molar mass of 12.01 plus the 1.01, or 13.02, and this is obviously much heavier than that, so I take the 78.10, divide by the 13.02, and I'm going to get a number very close to 6, 5.998, which statistically is 6. So my molecular formula is going to be 6 times the empirical formula, or C6H6. Number 32, you're again asked to determine empirical molecular formulas. You're given a molar mass of 162 grams per mole, and you're told your sample size is 0.8821, and the composition is 0.0220 grams hydrogen, 0.3374 grams phosphorus, and the remainder is oxygen. So I simply added the two masses from hydrogen and phosphorus, subtracted from the sample size of 0.8821, and that's how I got my mass of 0.5227 for the oxygen. So I'm going to go ahead and convert these to moles. So after converting to my molar amounts, here's my ratio. So my smallest ratio is the 0.01089 from phosphorus. So if I go ahead and divide, get my 0 in there, each of my molar amounts, I'm going to come up with the hydrogen 0.02178 divided by the 0.01089. It's going to be 2. The P is obviously going to be 1. And the oxygen 0.03267, 0.01089, I'm guessing that's going to be around 3, and it is. So H2PO3 is my empirical formula. So now if I go ahead and look at my empirical formula and what that would weigh, I would have 2 times the 1.01 plus the 1 phosphorus plus the 3 oxygen, and I get a molar mass of 80.99 for this empirical formula. So looking up here, it appears to be about half of the actual molar mass, and indeed the molar mass is 2 times as much. So then my molecular formula has to be doubled to H4P2O6. And we don't have to worry about whether that P2O6 is a polyatomic ion or not. We can just express it like this as our molecular formula. So number 33, you have a sample with a mass of 0.8138 grams, and they've analyzed and found the following amounts of carbon, hydrogen, nitrogen, phosphorus, and then you're told the balance is oxygen. And I know it kind of seems like a pain that if they've given you all the other amounts, why can't they go ahead and tell you the oxygen? And the point they're trying to make is that often this analysis is done by combustion. So the oxygen is the one you would have to do some calculating on. That wouldn't be just spit out to you with your equipment. So it is found to have a formula mass of 507 grams per mole. So same thing as a molar mass. And you're asked to find the molecular formula and its empirical formula. So if I go ahead and change my molar amounts, let me just pause while I do that. So here are my molar amounts, and so I carried each one to 4 sig figs because that was the amounts they gave me, all had 4 sig figs. So now when I find my smallest amount is going to be this 0.004814, which is going to give me a 1 for the phosphorus. And if I go ahead and divide the others, and I'll pause as I set this up. So now when I look at my molar amounts, I didn't come out to whole numbers. These aren't close enough to round, because if I look, what I see is 3.33 is about a third, 5.33, 5 and a third, 1.67, 1 and 2/3, and then 4.374, 4 and a third. So apparently my smallest subscript is not a 1 in this case. So now when I rewrite this, I'm going to go ahead and, oh, that's very funny that it's not taking my whole thing at once. I really have C 3.33, H 5.33, and 1.67, P1, and O 4.33. So I need to multiply this whole thing by 3 to get my empirical formula. So when I do that, I'm going to end up with an empirical formula of, so I come up with an empirical formula of C10, H16, N5, P3, O13, which is a big molecule, but if you remember from biology, ATP is kind of a big complex molecule. And then when I find its molar mass, it's 507, which is the same as the formula mass they gave me in the problem. So this is not only its empirical formula, it's also its molecular formula, which isn't so unusual with complex molecules like this. Empirical formula really isn't a very simple ratio. So question 34 looks a little overwhelming when you look at it, but I would encourage you to write things out in a statement if you can, because it kind of gives all your numbers a place to nest. So I've got a CHO compound that I'm trying to find the empirical formula for. I have 0.30 grams of it. I have all the oxygen I need to combust it, and I end up with CO2 and H2O. Now the key here is to notice that all your carbon ends up in CO2 and all your hydrogen ends up in H2O. So even though oxygen is in every reactant and product, we can still figure this out. What I'm going to do is take my 0.66 grams of CO2, and I'm going to convert that to moles of CO2, knowing that there's 44.01 grams per mole. So I'm going to get 0.014999 or 0.0150 moles of CO2, which means I also have that many moles of carbon, since carbon is in a 1-to-1 ratio in CO2. So now I know how many moles of carbon came from my original compound. I can do the same thing with the H2O, 0.36 grams, 1 mole, 18.02. I'm only going to come up with a bit smaller amount here, 0.36 divided by 18.02, 0.01999, so about 0.0200. Actually, I guess that's a slightly bigger amount, but this is my H2O. And now I have to remember that I get 2 moles of hydrogen from a mole of H2O. So I double this to 0.0400 moles of hydrogen. So I have my first 2 molar amounts to calculate my empirical formula. My problem is that I still need something to plug in for oxygen. So you could do this a couple of ways. You could add up the 0.66 and the 0.136 and figure out how much excess oxygen there was, and then figure out how much oxygen was in the CHO. Or I could convert my 2 molar amounts here. I could take the 0.0150, that's how much carbon there is, times 12.01 grams per mole of carbon, and I see that my 0.0150 is really 0.1802 grams of carbon. And if I do the same thing with my hydrogen, 0.0400 moles of hydrogen times 1.01 gram per mole is 0.0404 grams of hydrogen. If I add these 2 amounts together, I get 0.224 is the grams of hydrogen and carbon out of my 0.300 sample. So now if I subtract that, that means 0.0796 grams should be my oxygen. Well, if I have 0.0796 grams of oxygen, I'm kind of running out of space here. I know that 1 mole of oxygen is 16 grams. So if I go ahead and divide that by the 16 grams, I come up with 0.004975 moles of oxygen. So now if I go ahead and divide by my smallest molar amount, that 0.005, basically, 0.005, I'm going to end up with C3H8O as my empirical formula. Okay, number 35, I'm going to go ahead and power through this even though this video is getting a little bit long. You write your name with a piece of chalk that's pure calcium carbonate. How many carbon atoms did you use? So you're going to have to mass your chalk before and after, subtract that, and that's the mass used. And that is grams of CaCO3. So then you can change that to moles of CaCO3 by calculating the molar mass. And once you know the moles of CaCO3, you see that there is only 1 mole of carbon per 1 mole of CaCO3. So you can convert this to your moles of carbon. And once you know your moles of carbon, it's simply a matter of taking your moles of carbon times Avogadro's number, and you should know how many carbon atoms it took to write your name in chalk.